Okay, so last time we derived velocity and acceleration for polar coordinates. I want to generalize that to cylindrical coordinates today. So cylindrical coordinates I'm not going to ask him, but I assume Chris did it. You should all be more like Chris. Okay, so cylindrical coordinates. So there's a cylinder. So a point like this, we would represent in cylindrical coordinates. It's basically the combination of polar coordinates with a third axis. So this point here would be represented by an axis that way. That's ER, and the coordinate is R. And a perpendicular axis that way. How am I going to do this? So let's say that's a distance R. That's an angle theta, just like in polar coordinates. But then in addition, you have a third axis, and you use that to give the height. Okay. Can you follow what I'm getting at here? So it's polar coordinates plus a third axis. So you give your coordinates as R, theta, Z. And so if we want to calculate the acceleration of a point, I guess let's do velocity too. So a point whose motion is defined by R, ER, sorry, that's wrong, by R, theta, Z. Okay. Okay, so in that coordinate system, in the cylindrical coordinate system, the position vector is just R, ER, plus Z, EZ. Does everyone follow how that works? So if this is the point that you're interested in here, to get there, you just go a distance R along the ER axis. So this is the ER axis. You don't go anywhere along the E theta axis, and then you go up along the EZ axis. So you just go over along ER and up along EZ. Okay. It's the same as it was in polar coordinates, except now that you have to make a motion along the Z axis too. Okay, so if we want to calculate the velocity, that's the time derivative of the position vector. And this is a rotating coordinate system. What's the angular velocity of this coordinate system? Theta dot, and what's the axis of rotation? What? It's rotating theta degrees each. It's rotating as theta increases. It's rotating counterclockwise around the z-axis. Okay, so this omega is going to be 0, 0, theta dot. Okay, and the velocity vector in a rotating coordinate system is equal to the time derivatives of the components plus omega crossed with the position vector. This position vector we can think of as R0, Z. That's just another way of writing R, ER, 0, E theta, and Z, EZ. This first one we'll call the ER axis, E theta axis, and EZ axis. Okay, so what are the components dotted? If these are the components of the position, then dot each one of these components, and you get R dot, 0, Z dot. And then you're adding omega crossed with the position vector. Omega is 0, 0, theta dot, crossed with the position vector, R, 0, Z. And so the velocity vector is R dot and that's all in the ER direction, and then negative R theta dot, and then that's in the y direction, so that should actually be positive. And then in the z direction, there's no cross product term, but you have z dot. Okay, so generalizing from polar to cylindrical, the only thing that changes is we have this z dot term now that we have to deal with for the velocity. And now for the acceleration is equal to the components of the position double dot plus the angular velocity of the coordinate system dot across the position vector plus 2 times the angular velocity of the coordinate system crossed with the observed velocity vector, that's the dotted components of the position vector, plus omega cross quantity omega cross p. Okay, so what are these terms? The px double dot, py double, I should have written these as, since we're not using x, y, and z, let's write these as pr, p theta, and pz. Okay, so based on just looking at the position, what are the derivatives, the second derivatives of the ER? What's the second derivative of the ER component? Yeah, R double dot. And then the E theta component? 0. And then the Z component? Z double dot, yep. What's the angular velocity of the coordinate system dotted? We know that this is the angular velocity. So what do you get if you take the time derivative of the angular velocity vector? Yep. And then this one we already have. The time derivatives of the components of the position. And that was equal to just R dot 0 Z dot. Okay, so now we're ready to put this all together. So the acceleration is equal to R double dot 0 Z double dot crossed with, plus 0 0 theta double dot crossed with the position vector R 0 Z. Plus 2 times the angular velocity, 0 0 theta dot, crossed with the time derivatives of the position components, so that's R dot 0 Z dot, plus omega 0 0 theta dot, crossed with the quantity 0 0 theta dot, crossed with the position vector R 0 Z. Okay, so we have this plus the cross product of this second term. Do we have any non-zero values there? Yeah, the y component is, or the theta component is R theta double dot. You see that one? And then plus 2 times the only non-zero one is R dot theta dot. Plus 0 0 theta dot crossed with, here we have 0, 0, r theta dot. And this one comes out to be in the x direction. These were in the y direction, right? In the this one in the x direction is negative r theta dot squared 0, 0. And so that acceleration is r double dot minus r theta dot squared. For the theta component, r theta double dot plus 2 r dot theta dot. And then for the z component, z double dot. Okay, so how does that relate to the acceleration we got for polar coordinates and, well, and also the velocity? Yep, that's all it does. And why isn't there any weird stuff going on with the z component? Why is the z component, it just shows up in velocity as a z dot, in the acceleration as a z double dot? Well, the other two are like Cartesian axes too. They're just changing their orientations. But that z-axis, because the rotation is about the z-axis, it doesn't change its orientation. So it behaves like we're used to with a coordinate system. It's just the r and the theta axes that behave differently than we're used to. So there's a z-axis added on that isn't changing its orientation. Okay, let's do an example. Okay, so let's say a particle is traveling a helical path. And if we think of the particle as being here, the ER direction is this way. The E theta direction is perpendicular to that. And the EZ direction is up. So let's say that this particle travels a path where travels in a helical path. So R of t is equal to 5. So what's that saying physically about this path? It's not changing over time. So physically, if you're just describing in words what this particle is doing, what does that mean? Yeah, right. It's not changing distance from the center of this helix. And then theta as a function of time is equal to 2t. So that tells you how quickly it's traveling in this circular path. And then z as a function of time is equal to 0.5t. So if the particle has a mass of 0.01 kilograms, what's the force vector? The net force vector on the particle as a function of time. Well, we need to use Newton's second law, so we need to figure out the acceleration based on this motion. The acceleration is equal to r double dot minus r theta dot squared. Then the theta component is 2 r dot theta dot plus r theta double dot. And the z component is z double dot. Okay, so r dot, what's that equal to? 0? Do we have any, yeah, what's r double dot? 0. Theta dot, theta double dot, 0. Z dot, z double dot. Okay. So now we just have to plug these into this formula. The acceleration vector is equal to 0 minus 5, that was r, times theta dot squared then for the theta component, we have 2 times r dot, which is 0, times whatever, it doesn't matter, plus r, which is 5, times theta double dot, which is 0, so it doesn't matter. And then for the z component, we have 0. So we end up with an acceleration that's equal to negative 20, 0, 0. So that looks like a constant. That looks like a constant acceleration vector, but this thing obviously doesn't have a constant velocity vector. So how does that make sense? That's right. So the orientation of that ER axis is always changing. So this is always 20 pointing toward the center of that helical motion. And how would you describe that acceleration? That's just the centripetal acceleration of the circular part of that motion. Okay. And so then Newton's second law says F net is equal to the mass times the acceleration. So that's equal to 0.2 negative 0, 0 newtons. it's always pointing towards the center of the circular motion. Any questions about that one? Okay, so let's change it a little bit, and I guess let me have you go through one of these. So let's say you can think of it the same way. So there's a new helical motion. So this time r is equal to 5t. Theta is equal to 2t squared. And z is equal to 0.5t squared. What's F net on that same particle? As a function of time. Okay, so I did these as vectors. Okay, so r dot is 5. Our double dot is 0. Theta dot is 4t. Theta double dot is 4. Z dot is 1t. Z double dot is 1. And so the acceleration vector, we have r double dot minus r times theta dot squared for the theta component. We have 2 times r dot times theta dot plus r times theta double dot and then for z double dot we have 1. So minus 20 t cubed. What? Oh, I didn't square that. Yeah. Thank you. 16. What is it? 80 t cubed. Then 40 t plus 20 t, so 60 t. 1. And then Newton's second law says the net force vector is equal to 0.01 times this. So negative 0.8 t cubed, positive 0.6 t, 0.01. Any questions about that? So the next thing we're going to talk about is superimposed motions. And so here's an example. So let's say that you have a rod fixed to the wall, and there's a rotating piece on the rod that's rotating that way. And then connected to the rotating piece is a disc that's rotating this way. So let's say that it's rotating. This is going 5 radians per second. It's speeding up at 15 radians per second squared. Let's say that the piece that it's mounted to is rotating at 20 radians per second. And we want to know at this instant what's the acceleration of that point P. Well, this is a case where one motion that's easy to describe, easy to do the calculations for, is riding on another motion that's easy to describe. And together, like, there's no way to sort that thing out by the approaches that we've used so far. To just try to figure out what this compound spinning motion is going to do to that point, there's just no way to sort it out. But if you identify which one of these is riding, which one of these motions is riding on top of the other motion, so think of this as the horse, and this disc is the rider. You can fix a coordinate system on the horse calculate the motion of the rider with respect to the horse, and then use the approach for rotating coordinate systems to account for the rotations of the horse. Okay, so for this example, the coordinate system, so if we call this body 1 and this body 2, fix the coordinate system to body 1. And then calculate the acceleration of P that's observed by the coordinate system. Okay, so so our coordinate system is going to be fixed by 1. The only motion that is happening relative to this coordinate system of this point P is a circular motion. And that's easy to do the calculations for, right? That's not the true acceleration because that's not yet taking account of this spinning. But we'll first calculate that observed velocity and observed acceleration, and then we'll account for it. Okay, so what's the observed velocity of that point P? That's just a circular motion, so it's going to be omega cross r. What's omega for this disk? Well, I didn't give coordinate axes, but so let's say that our coordinate system, let's choose this, this, and this. Okay, so x, y, z. And it's rotating with body 1. So what's omega for the disk? About what axis? About z, right. So, yeah, so it's 0, 0, negative 5, crossed with, what's the r vector? Did I give a radius? No. I meant to. Okay, I need to. So let's say that this radius is 0.4 meters. Okay, so what's the r vector for P? That's right. Yep. 0, negative 0.4, 0. And so the observed velocity is negative 2, 0, 0. And now, how do we calculate the observed acceleration? Yep, that's right. So alpha cross r plus omega cross quantity, omega cross r. What's alpha? Z, yep. 0, 0, negative 15. Same r vector that we had before, so that's 0, negative 0.4, 0. And then omega is 0, 0, negative 5, cross quantity 0, 0, negative 5, cross 0, negative 0.4, 0. Anybody have that in the calculator? Say it again. Okay. So this is meters per second. This is meters per second squared. Okay. But now we have to account for the fact. So far this is the only tricky thing about this has been forgetting for a, ignoring for a second that this body 1 is rotating at all. But now we have to account for the fact that body 1 is rotating. And so we're going to use this new approach for rotating coordinate systems. So the acceleration of P is going to be equal to the component's double dot, which you can also think of as the observed acceleration in the coordinate system, plus the angular velocity of the coordinate system dotted, crossed with the position vector, plus 2 times the angular velocity of the coordinate system, crossed with the observed velocity, plus capital omega cross quantity capital omega cross p. Okay, so A observed is negative 6, 10, 0. What's the angular velocity dot of the coordinate system? 0. Yeah, because this is, well, I didn't give anything. This is constant. Plus 2 times the angular velocity of the coordinate system. What's that? Very good. Yep, negative 20, 0, 0. Crossed with the observed velocity. So that's negative 2, 0, 0. Plus omega crossed with the quantity omega cross, and what's the p vector? The position vector? Yep. It's the same as the r vector in this case. That's not always the case. It depends where the coordinate system is located. So 0, negative 0.4, 0. This one goes away because the cross product of 2 parallel vectors is 0. So you get negative 6, 10, 0. Plus negative 20, 0, 0, crossed with 0, 0, 8. Negative 6, 10, 0, plus 0, positive 160, 0. And so you get negative 6, 170, 0. Any questions about that one? Okay. I want to just say one thing. What if you fixed the coordinate system to the disk? Does it matter where you put the coordinate system? And the answer is yes. You always need to fix the coordinate system to, so there's always this one object that is being ridden, the horse, and there's always one object that's riding it. The rotation of one of them depends on the other one. You know, the motion of one depends on the other, but that's not true the other way. Okay, so no matter what this disk was doing, the motion of this body 1 would not change. You have to put your coordinate system fixed to the one that's independent. Yep.
So if you had, like, let's say where it's in the wall, if that was spinning as well, if you still do the farthest out one?
So if you had 3 things that were spinning, you would have to back your way out piece by piece. So you do what we just did, and that would give you the observed acceleration in this new coordinate system, and then you'd have to account for that rotation. And you can do that as many times as you need to, but in this class you'll never need to do it more than once. Okay. The coordinate system always should be fixed to the horse. Okay, that's all. Are there any holidays before Wednesday I should know about? Yeah. I'm sure you can.
I'm sure there's like National Donut something.
Yeah, you're right. I'm sure there's a